So I'd like to look at a concept that's called the magnetic vector potential. To get started, I just want to remind you that we have a condition on the electric field where we know the divergence, which is equal to the charge density over epsilon 0, and we know the curl. The fact that this curl is equal to 0 allows us to represent the electric field in terms of a potential. So remember, you take the negative of the gradient of that scalar potential, and that gives you the field. In terms of the magnetic field, we don't have zero curl. So what that means is that we can't find a simple scalar function to obtain the B field. So in magnetostatics, we have this condition where the divergence of B equals 0. What that meant, you remember, is that there are no magnetic charges. Thus, there are no magnetic monopoles. What this means is that we can find a different kind of potential, namely a magnetic vector potential, and we'll call it A of R. This A of R will generate B by taking the curl of A. Now, if you look at the units, we know that B has the units of Tesla. This operator here is 1 over the distance, 1 over meters. So that means A has the units of Tesla times meters. So given this relationship between the vector potential and B, let's take the divergence of B, and we immediately have the divergence of this quantity here, which is the curl. And if you remember, the divergence of a curl is always 0. A of R protects the condition that we have no monopoles. This condition here, where we can have B generated from a vector potential, is actually a corollary of the Helmholtz relations. So if the divergence of a vector field is identically 0, which it is, then that vector field can be written as the curl of some vector potential field, and that's what we call A. That the curl of a gradient is equal to 0. So that brings us back then to the curl of A being basically the same, even though we've added this function here. If we take the divergence of this new A, if we take the divergence of that, again this distributes, and we end up with the divergence of A times the divergence of this gradient. This operator here is del squared, the Laplacian. What this means then is that we can always find a scalar function f such that the vector potential is divergence-less. So for the above, let's force this divergence of the new A, which is this quantity here, and so therefore is equal to this divergence of this sum. We'll force it to be equal to 0. What that means then is, if you look at this, we have the divergence of the A old is minus the Laplacian of f. So that just comes about from solving this, or putting this on the other side of the 0 equation here. Theoretical physicists have a habit of just saying, I can solve it. We're going to say this is an equation that we can solve, and so there exists a solution. Since we don't know A anyway, we'll boldly set A equal to this A nu. Now we have the condition that we wanted for this. This is the A nu, that we have the divergence of that equaling 0, which is protecting us as before. When you set this new A nu equal to the one that has the 0 divergence, you call this the Coulomb gauge. Why do we do this? Well, it simplifies many equations involving the vector potential. Using the Coulomb gauge is just a simplification. Let's consider using curl of a curl. We have then the curl of B. That will be equal to the curl of, remember this is B right here, so curl of A. And if you remember, there's a expansion of this where we get the gradient of this function here, which is a scalar, minus the Laplacian of this vector here. But remember that del cross B is equal to mu 0j. This was Maxwell's equation. If you look at this, then you can solve for the Laplacian operating on A, and this will be equal to the minus mu 0j. Okay, remember this equation here comes about because this is 0, this term here. So we're left with this equation, which is equivalent to this one. Well, this equation here is called Amperes Law, written in terms of the vector potential A. This is a vector equation. It has three components, and if you look at this Laplacian as a function of x, y, z, say, is equal to some quantity here, this is like the Poisson's equation, and this would be like for a charge distribution rho. And if you remember, what we did there was we took the Laplacian of a scalar function, and we got, of course, a scalar here. This led to this form of the potential in terms of rho and a gradient over the volume. Therefore, the vector potential can be calculated from the current J in a manner similar to this. But there are three equations for each component of A. And so I've expanded this out in terms of the form that we have here for the scalar potential. Each one of these is like that. We have a x component here, which is related to the x component of J, the y, y, z, z. Instead of getting just one equation, we have three for each component of the vector potential. But it's the same form that we had for the electrostatic potential. So let's look at Amperes laws for A of R. If we look at the different conditions where we can evaluate A sub R, they're just similar to the conditions we have representing currents. So remember, we have J for a volume current, we have K for a surface current, and we have I with dl prime, of course, for a line current. Each one of these is a form of Amperes law for the vector potential A. And don't forget that each equation has three components. These solutions do require that the currents go to zero at infinity. Just like for the electrostatic potential, we had to have charges where the charge density went to zero at infinity. And that's what I say here, that the requirement that rho goes to zero at infinity. This is a promise we make when we use capital A. Another note is that if you look at the direction of A, it's always parallel to the v, which is the motion of charge, to the direction of I, dl, k, and j. In other words, A is always parallel to the direction of motion of the current. If we have, for example, this equation here, A is going to be proportional to the dl prime unit integrated over the curve C. If we look at that, then the A sub r's is in the direction of the current element dl prime. And the same goes for A in terms of a surface current, and the same for A in terms of a J. So when you take this integral, you end up with an expression that has a direction which is in the direction of the current flow. This second note then guarantees that we have a relationship with the direction of A here. We have the A parallel to these different velocities or directions of flow. If you take the curl of A, that always gives you a vector B, which is perpendicular to those currents. And that's what we've used before in terms of the relationship B to the direction of these current flows. There's a useful idea here, is that if you were to take the A vector and integrate around a loop, so we integrate around a closed loop C, then we can express that in terms of a surface integral and the curl. So this is basically Stokes' theorem right here. So if you do that, then remember this is B, so this surface integral is equivalent to this one right here. But this is the definition of magnetic flux through the surface S. So we can then say that the line integral of A around a closed loop C is equal to the flux of a surface that's bound by C. The direction of the line integral around C relates to the direction of ds via the right-hand rule. So let's determine the magnetic vector potential of an infinitely long wire carrying a steady current I. We know that the B field is equal to this expression here, where it's mu 0 I over 2 pi s. This is B of s, like that. And this is the direction that it gives by the right-hand rule, which is wrapping around the wire. It might seem appropriate to just use this equation here. It's a line current, so we would expect it to have an I and a dl prime. So this is what I gave you before for a line current. So we take current element I dz in the z direction and just integrate it from minus infinity to plus infinity. We did that using the Biot-Savart law. This breaks our rule because we have infinities here. The worst thing that can happen is that in fact it generates an infinity. And if you actually go through this and do what I've shown you here, we will end up with an infinity. And I just notice here that I have another mistake. This is the integral over the current loop. Current loop in this case is an infinitely long wire, so this goes to infinity, this goes to infinity, and that gets us into trouble. Let's take the case where instead of an infinitely long wire, we're going to take a finite length, so there are no infinities. This is very similar to our derivation of B using Biot-Savart for a finite wire. There we considered an element dx x hat on the wire and a point P at distance s. So let me just draw that. Here's the finite wire, and we took a point P above the wire at distance s, like that. So that's one of the problems we arrived. If we have a finite wire, then let's say it goes from minus L to plus L, we can write A in terms of a differential first, dA. It will be equal to x hat mu 0 I over 4 pi. So far okay. This is what we're using, by the way. We're using this equation here, but that should be a C. We're getting A sub I, this prefactor, dl prime over funny r. Well, funny r in this case is going to be the distance from the wire plus the position x squared to the 1/2 power. And the dl will be along the wire dx. And the direction, of course, is in the x hat because dl is along the wire. So dx x hat is equal to dl prime. If we now integrate, so we just put in the integral from minus L to L of this quantity here, then let's take that, just the integral. What that is equal to is 2 times the log of this quantity right here. So all this is the integral of this expression up here. To find A, we just put back the rest of this, so we have x hat times the prefactor times this quantity right here. Stopping right here, this is the exact solution for a finite length. The other thing to notice is that A is in the direction of the current flow, which is x hat. We have found A for a system that is of interest, which is this finite wire. It does not give us the expression for an infinite long wire, but we can come close to an approximation by just letting L get very long. So if you take this expression here and make L much, much larger than S, then this becomes L plus L. So we get 2L right here divided by S, the log of that quantity here. Putting it all back together again, we can separate the ratio here to x hat, so it's again in the direction of the current, the prefactor with a 2, and then this difference between log 2L minus log S. So the S dependence of this expression is right here. And this is an approximation. If you're close to the wire, S is very small compared to L. This would give you a good approximation for the A. So let's take the curl of this approximate A and see what we get. Here's the expression for the approximate A. We take the curl, and because of the symmetry of this problem, we're going to take the curl in cylindrical coordinates. I'm going to let x equal z, so this is the normal axis variable for the cylindrical coordinates, but just imagine that's x. A depends on s only. So taking the curl of A, the only term that survives is the phi component, and it has a minus sign here. The reason that's the only one is because this is the only component of A which depends on S. In terms of the other components, we don't have any S dependence. Taking the derivative with respect to S of all of this, you'll notice that this is a constant, and here's where we have S, and so we end up taking the derivative of log of S. So when you do that and take into account this minus sign and this one, you end up with the function mu 0 I over 2 pi s in the phi direction. This was derived for an approximate A, and in principle it only holds for L much larger than S, and that's what we meant by close to the wire where S is small compared to L. But surprisingly, it's the same thing we got from Biot-Savart or Amperes Law for an infinite wire. It's somewhat disappointing, but at least the fact that we had to only get an approximate value and that this turns out to be correct, but what it shows is that we at least got our algebra correct. If we look at the curl of A, I just wanted to show you how we ended up with just one term. If you look, remember x is equal to z, rho is equal to s. And so it turns out that this is the only non-zero term in the curl. All of these other things do not depend on s, or they just are zero to begin with. Well, let's take another system, and that is the magnetic vector potential for an infinitely long solenoid along the z-axis with little n turns per unit length, radius r, and steady current I. So again, we have an infinite dimension, the length of the solenoid. We have to do a tap dance again. Take advantage of the connection between magnetic flux and A that we derived earlier. Remember, if we take the line integral of A around a closed curve C, which then is equal to the surface integral by Stokes' theorem of the curl, which is equal to the flux of B, then we get this relationship here. So I'm just repeating that argument. Well, we know what B is inside. It's a constant field in the z-hat direction. And because the current is phi-like, so it goes around the cylinder, or whatever you want to call it, in the phi direction, A only has a phi component. Remember, A is going to be in the direction of the current. If we take a C inside the solenoid, so we have this C inside where the radius is S, which is less than the R of the solenoid, then we're inside, and we have a path which is normal to the z-hat, and z-hat would be along the axis of the solenoid. We go back to our integral of A over dl around C, and now we're inside. That's equal to A phi times 2 pi s. And the reason is because A is in the direction of the current, it's parallel to dl, and so we can bring it outside and end up with the phi component of A, which is in the direction of the current, times the area of the loop, which is 2 pi s. Putting that into the flux equation, we end up with this quantity here, the flux. And what is the flux? Well, it's B, right here, this is B, times the area of that loop, the area of the surface enclosed by C inside. Solve that for A phi, and you end up with a simple function, which is mu 0 ni over 2 times s. And remember, this is for s less than r. So now let's go outside, and here we have the same expression for the A integral around the closed path C. For the same arguments, it's equal to this. And remember, s is this distance here, which is greater than r. So go through the argument of the flux again, and now what is the flux through this path? Well, realize there's only flux inside. There's no flux out here. And so since this distance is r, the area of the place where we have flux is just going to be pi r squared. Taking B here, multiplying by pi capital R squared, B only extends to the distance capital R. We can now take this equation here, so A phi 2 pi s is equal to this quantity here, and solve for A sub phi. And so we end up with mu 0 ni capital R squared over 2s. Outside, A changes s dependence from inside. Inside it's linear with s, here it's 1 over s. And this is for outside. Even though we have an infinite extent, by using the flux, we're able to get an A. It's somewhat puzzling, though, because we had to use our knowledge of B to get A. Quite often, we're trying to get an A and then find a B. So I just wanted to point that out. So let's assume that we have an A that we've just derived. Remind you, we used B, but let's find B from A and see if at least going in a circle we get the same thing. we're going to take the curl of A, and to do that we're going to use cylindrical coordinates. And for that we look here in terms of the curl of A, and remember we only had a phi component that depended on S. This curl here has rho in place of S, so just remember that rho is equal to S. To form that component of the curl, we're going to end up with the z hat direction only, and the value is 1 over S times the original A plus S times the derivative of A with respect to S. Let's go back to the inside. So here's our A inside, phi component only, and this was the expression we got for the value of A in the phi direction. We put it into our curl to get our B, and so we have 1 over S, it's this 1 over rho up here, times A sub phi plus S times the derivative with respect to S of A sub phi in the z direction. So we substitute in our A sub phi, which is right here, and we take the derivative with respect to S and multiply by S. Well, you can see you have identical terms here, so the 1/2 here and the 1/2 here disappear, and so we end up with this equation for B inside, which is exactly what we'd expect and what we used to find A. It's the mu0 little ni in the z hat direction. The important thing is that we started with an A, which is in the direction of the current, and it gives us a B, which is in the direction of Z. And the right-hand rule operating on the windings of the solenoid would have given us the same result. So let's go outside. Here's A outside, which we derived. Again, it's in the phi direction. So we have the same situation where we're only going to have, this should be 1 over S. So we have the same expression for the curl. It's 1 over S times the phi component of A plus S times the first derivative of A phi with respect to S. And again, it's in the z hat direction. If you go ahead and do this, you have the function mu0 ni r squared to S. All of this is multiplied by 1 over S, which is this factor here. It won't matter because what we're left with inside, if we do all the operations here, we're going to end up with 0. And that comes about because this S here converts this to 1 over S. It has a minus sign. So we end up with a term that looks exactly like this. So the fact that I left this off really doesn't matter. It ends up to be 0. That's exactly what we wanted. It's basically telling us that even though we use the flux to get the A, it is the correct A in terms of generating the B fields that we wanted. Since we've only got a phi component, if you take the divergence in cylindrical coordinates, the only term that survives is this one right here. It's 1 over S times the partial of A with respect to phi. If you look at our A's, if you take the derivative with respect to phi, there is no phi dependence, both inside and out. So as a result, we do in fact preserve our condition that the del dot A is equal to 0, which you recall was the Coulomb gauge. This is sort of a summary of some of the findings that we've had so far, and that is that if you take magnestatics, there are 3 fundamental quantities. There's the current density, there's the magnetic field, and there's this vector potential. These are all interrelated, and if you know one of them, the other 2 can be calculated. This table here summarizes the relations. So let's suppose you know one of these, J, B, or A, and then you want to determine the others. So if you know J, then you can come over here and form B by this equation right here. We've talked about this before. This is Maxwell's equation, the integral form. This is delta R being the funny R. So this quantity here is the funny R hat, and this is funny R squared. Likewise, if we have J, we can form A by the equation that we derived, mu0 over 4 pi, and so on. This is the volume integral, so this is an integral over tau. Same here, this is an integral over tau. If you know B, then we can calculate J just by solving for J from the fundamental equation, which relates J and B right here. So if we do that, then we have an expression for J in terms of B, and likewise we can find A from B from this equation here by using this quantity here, which is related to J. So this kind of goes in circles. Finally, if we have A, we can form J by taking the Laplacian of A. This is a vector here. J is a vector, so we've got to have three components. And likewise, we know that from the definition of A, this is equal to B. We have Amperes Law giving us this equation, B sub R giving us this equation, and so we can relate these together in terms of a single value here giving us the other two quantities. This is a summary of the boundary conditions. Most textbooks derive these, and I encourage you to look at those derivations, but at a minimum we want to know what these boundary conditions are. So this is boundary conditions on the magnetic field. Here we have a interface that has a current sheet where we'll just let K be represented by this vector here, but it could be different all over this sheet. And so if you take a point on the sheet and then look at just above and just below the sheet, then the first boundary condition is that the perpendicular or normal component of the magnetic field B is continuous at a surface current. And this of course includes the trivial case where K equals 0. So here's the way we write that. The boundary condition 1 on B perpendicular is that we have B above, B below, perpendicular, perpendicular are equal. Sometimes we write it like this, where we take B above minus B below and then dot it into the normal vector n hat, where n hat is a unit vector perpendicular to the surface. These are equivalent because when you take the dot product you end up with a perpendicular component. If you have the same condition here and you take a look at the tangential component of B, it's discontinuous, and that discontinuity is going to depend on the current density, the surface current density. So this is the second boundary condition, and this is on B parallel or tangential. And so what you have here is that the tangential above, tangential below, with the minus sign, is proportional to the current density, and it's mu0 times K. Okay, now this is the magnitude of K. This is not the vector K. You can take these two boundary conditions and combine them, if you wish, into this format here. So these are the vectors above and below, and it's equal to mu0, the vector K, crossed into n hat. If you go through the parallel and perpendicular components of this, in terms of what you get over here, you can see that they give you BC1, BC2. Personally, I think this is interesting, but the BC1, BC2 alone are usually more useful. So what about A? We've got the same condition here, and we're looking at A on the two sides of the current sheet. The first boundary condition is that the vector A itself is continuous across the interface. And this is all components. BC3 on A is A above equals A below. If you were to look at this in some way where you have your A vector below and then you get an identical vector above for the A. And remember, A is supposed to be in the direction of K. The last boundary condition is also on A, and that's with respect to a normal variable. So you have a x, y, z, but there's also a quantity which is a variable normal to the surface. We call that n. We find that the partial derivative of A above with respect to this variable n minus the same thing below is equal to minus mu sub 0 K. If you remember in terms of potentials and the vectors of the E field that are generated by taking the derivatives, we had a very similar expression, whereas this is a vector equation. In the case of the scalar potential, it was a single derivative, which is like the gradient, which gave you a normal component of the E field above and the normal component of the E field below. We're doing A. A is a vector, so if you take the partial with respect to this, you get a vector, and so on. So next time, we're going to talk about multiple expansions of A, and that's going to lead to a very useful concept, and that is the magnetic dipole moment.